Hey guys, so today we're going to be doing round 665, which is a div 2. Before I start, there are two things I want to say. One, we're going to start, in order to make Screencast better, I'm going to try to stop using templates. Like instead of that, I'm just going to write out a for loop like a normal person would. We're going to keep LL because that preserves my sanity, but other than that, we're fine. And also, we're going to start, this is kind of a tradition, I guess. We're going to start honoring everyone essentially. So we're going to take this number and we're going to put it in our template. So what this means is that every individual subscriber is going to contribute 24 bytes to my memory count. And the ultimate goal is that we're going to try and make it so I get a memory limit exceeded verdict because I'm using too much space in these arrays. Yeah, anyway, that's enough of an intro. Let's get started with the round. Okay, so first reading number of test cases, just reading the input, then let's see. So we're going to make it so the bigger one is, oh, okay. So n is positive, and I want to make it so the absolute difference between the two distances is equal to k. So let's see. First of all, it has to be the same parity as the distance between A and O, and then after that, we can achieve any even number that's less than any number that's the same parity and any number that's the same parity and also has to be like the maximum distance we can achieve is 4 because either we have a point between them or we have a point like on the end. And if it's on the end, then no matter what, it's going to be 4 away. So first, if they're not the same parity, n mod k is not equal to, no, m mod 2 is not equal to k mod 2. Then plus plus n, and this equals 1. Then what we're going to do is, it's good enough to only increase, so ants plus equals, it'd be max 0, then the number we would have to increase is k minus n. Let me just print it. Test it in OBS. 0, 3, a million, 0, and 0. Okay, perfect. Open the rest of these. Oh, that was quick. Good that there are no queue issues. We got multi-tests. So two sequences, A and B, all are 0, 1, or 2. Okay. That's slightly weird. Okay, so we're going to just read this in as arrays. We're going to read x, y, and z as elements of A, and then the second x, y, and z as elements of B. So let's just do some casework on what like what everything gives us. So if we have a 0, 0, we get 0. 1, 1, 1, 2, 2, 2. 1, 0, 0, 2, 1, 1, 2. Wait. 2, 0, 0. Then these are the ones that will be negative. So we have 0, 1, 0. No, wait, sorry. These are all 0 because it's 0 if they're equal. So 0, 1, 0. Then 1, 2. Negative 2. Then 0, 2, 0. So basically it's only these that we care about. So we want to maximize the number of these and minimize the number of these. And how do we do that exactly? How do we do that? Okay, so first of all, let's just maximize the number of these. LCT equals min A2 B1, and this equals 2 times CT. Then A2 minus equals CT, B1 minus equals CT. Then we want to make as few of these matches as possible. So what we're going to do is we're going to pair as many other elements as we can with 2's and B. So LLA rest equals AO plus A2. Then we're going to pair as many of these with 2 as we can. B1 equals min max 0. No, 2 minus A rest. This should be 2. LO B rest equals. Then we want to pair as many 1s in the first sequence as we can with literally anything else. So that would be B0 plus B1. A1 equals max. A1 minus B rest. Then whatever we have left, we're forced to take. So ants minus equals 2 times min A1 B2. And that's essentially it. Come to that. What? 420. Okay. Let's be a little more cautious, so we'll test it on some other sample. Let's just say we have many of these. So 0, 5, 1, then 0, 1, 5. Answer here should be -8. No, wait. Yeah, multitest here. Also -8. How does that work? Oh yeah, because we can get rid of one of the -2's. Okay, that looks right. Hopefully it is. There may be some casework that we missed, in which case we'll just wow, that was instant. Nice. Okay. Like it it judged my submission faster than the page loaded. That's kind of cool. By the way, if you're noticing the the new warning messages. That's just because I have new compiler flags. Like I make it so it'll debug stuff for me, kind of, which is nice. Because basically the flag w all, which will it's not exactly going to debug things. It's just going to warn me about a lot of things. Okay, mirror array. You're given an array, all AI integers and greater than 0. You can choose 2 different indices. The minimum element of the whole array. Okay. So guess first of all we can use all. Wait. Let's say it's some sequence like 1, 4, 3, 2. Now the GCD of everything except for these is 1, but that doesn't matter because we can use the 1 to sort this however we want. For example, let's swap the 1 and the 2. Now we have 2, 4, 3, 1. Now we'll swap the 1 and the 4, so we have 2, 1, 3, 4. So now we put the biggest element at the end, so now let's do the same thing for this. Then we'll just make it so 3 is here, then we'll do the same thing for this and make it so 2 is here. So anything that's a multiple of the minimum element, we can sort. And anything that's not a multiple, then there's no chance of it ever, like if it's not a multiple of the minimum element, there's no way its GCD can ever be the minimum element, like with any element, so we can't touch it. So what we can do is we can relatively sort all of the elements that are multiples of the minimum element, and then see if the whole array is sorted after doing that. So first of all, let's keep track of the indices and the values themselves. So now if min value equals 29 plus 5, doesn't matter. Min v equals min v AI. Now if AI mod min v equals 0, that means it's a multiple, then add it to a list of indices and also add it to the list of values. You'll see why I'm doing this later if you don't understand right now, because this is a simple way to sort everything. Then sort everything, then for, now we're going to go to the vector size, and it's guaranteed that these two vectors have the same size because like we just add to them both at the same time. So now we make a indices I is equal to values I. And what this is gonna do is, for example, take this array 4, 3, 6, 6, 2, 9. It's going to 4, 3, 6, 6, 2, 9. So these are the only elements we can sort. So all we're going to do is we're going to sort these elements, and since we can't touch the other ones, we're going to leave them in place. So we're going to change the array to 2, 3, 4, 6, 6, 9. And that's what we're going to do. So now we're going to check if it's sorted. or if it's not sorted, then there's some inversion between adjacent elements. False. Okay. That's fine. What? Okay. And all this makes sense. Slight delay in the queue. There are quite a few pretests here, but we're good. We're good. So now let's continue. We're given a tree, a graph problem. Each integer must be greater than 0. Product of all n-1 numbers should be equal to k. Number of ones among all n-1 integers must be minimum possible. Sum of the numbers on the simple path from node U to node V, so let that be a distribution index of the tree. Okay, so my general idea is, first we need to minimize the number of ones, but then what we want to do is we want to stack a single node as much as possible. Okay, wait, let's just make sure we have this right. So we're given the prime factorization. Doesn't really matter that they're prime, it's just all these numbers multiplied to k. Actually, it does matter that they're prime. That way we can't divide them any further. So let's say we have some tree like this, for example. And we have the numbers 2, 2, let's just say we have a bunch of 2's. 2, 2, 2, 2, 2. So k equals 2 to the 10th. Alright, so to minimize the number of ones, all these numbers have to be at least 2. 2, 2, 2, 2, 2. But then notice that, like, no matter what happens, everything is going to pass through this path. Right? And when we multiply a big number, like let's say we multiply 7 by 2 versus multiplying 5 by 2, then it increases by 7, but rather this increases by 5. So it's better to multiply a big number by something than a smaller number by something. So my idea is we basically just want to stack a single node and make it as big as possible. And then, yeah. So what we're going to do is we're going to count the number of paths that passes through each node. This is called contribution to the sum, and it's kind of a useful technique for doing things like this, because the answer is just the number of paths that go through each node, like number of paths that go through each node times the value. Now that itself is kind of obvious, but maybe coming up with that isn't, so it's a good trick to think of. So essentially we're going to stack this node and we're going to make it equal to 2 to the 6th equals 64. And that way we'll still have the whole thing be a product, the whole product be k, we'll minimize the number of ones, and we'll do everything else. Yeah, okay. So first what we're going to do is we're going to read the tree. Vector LL, edges, big number, 10 to the 5th at most, so C to n. That's just standard stuff for reading in a tree. And 0 indexing. Okay, now C into M. for we're going to reverse it so the biggest numbers are first. Okay, now we're going to count the number of paths. And the way we count the number of paths is, first of all, there's a path that goes to this vertex. Then, well, the number of paths that end in this vertex is like the number of paths that, like, for example, one of the endpoints is this is n, because there's a path from this vertex to every other vertex on the tree. So we have n plus, and then essentially there can be a path between any other two vertices in its what is it? What is it exactly? That's a good question. It would be like for each edge that goes out from it. Let's say like for example, this has subtree size 7, this has 5, this has 2, this has 4. Then there are 7 ways. There are like 7 times 4 ways to go from here to here. There are 5 times 7 ways to go from here to here. 5 times 2, 2 times 4. And we also need to consider 2 to 7 and 5 times 4. So it's essentially pairing all things together and then multiplying them. But that's annoying. So there's a better way we can do this, and that's essentially we're going to count both 5 times 4 and 4 times 5. And then we can divide by 2 since we count both of these twice. Then divide by 2. So that way, the answer is just and we're also going to, so the answer is just like, let's say the sum is actually it's easier than that. Actually, we can subtract out the number of paths that don't go through. We can subtract out the number of paths that don't go through this vertex. So we have n times n minus 1 over 2 paths in total. Then we subtract out, like in this subtree, we have 7 times 7 minus 1 over 2, which is 7 choose 2. This is a well-known formula. Here we have 4 times 4 minus 1 over 2. Wait, no, sorry, it's, yeah, 4 minus 1. Because for every vertex we pick, we have 3 others that it can go through without it being going through this node. So essentially what we're going to do is we're going to write a DFS, void DFS. Actually, we can make it a long one. DFS LL vertex parent. So LL total path equals n times n minus 1 over 2. This is fine because it's long. Eventually we'll do, and also we have the mod here already as 10 to the 9th plus 7, which is what we want. So now for every outgoing edge, if it's not a parent, LL subtree size equals 1. Subtree DFS go down, then subtree size plus equals val. Total path minus equals the number of paths strictly in that subtree. Then everything above is not in this subtree. So that's like, for example, if we rooted the tree and we were here, then this would be everything in the parent component that's, say, above it, whatever goes on here, since it's basically n minus whatever we have down here. So let's do that. Equals n minus subtree size, total path minus equals above times above minus 1 over 2. Same formula. Then we return subtree size so we can continue using it. So we're going to say if so if m is less than or equal to n, then we don't multiply anything because we're just going to use each prime factor in a different vertex. So let's n path v equals total path mod mod. Then we can also we'll DFS from the root since it doesn't actually matter where we DFS from. Then it doesn't actually matter the nodes we use, so we can just sort n path and reverse it, so now it's in decreasing order. Then for ants equals ants plus n path I times what is it? A I mod mod, and well, that's just it. We'll just count the sum of those. Contribution to sum. Otherwise, LO rem equals m minus n. LO product equals 1. I less than m plus 1. No. Rem plus 1, I plus plus. We're just going to make the first thing and make it as big as possible. Prod equals prod times AI mod mod. Then ants equals ants plus prod times prod times n path 0 mod mod, just regular modulo arithmetic, n I plus plus. Ants equals ants plus a I plus rem, since we've already used the first rem elements, times n path I mod mod. Then we're going to do that, and let's test it. And it crashes. Damn it. Okay. What are we doing wrong here? So, first of all, we do have multi-tests. Alright. Because I need to. It's always a good idea to make sure we reset the global variables, or just don't use them. Edges we do reset. We do need them for the DFS, unless we want to use lambda functions. Let's not, that's kind of confusing. So n path we don't need to reset because we're not relying on previous values. And edges we reset now. Um, 20, nope, that's wrong. What's wrong with that? Okay. Oh shoot, we're putting them on edges. Okay. Well, that's kind of annoying. Okay, in that case, it's actually a lot simpler. Okay, first of all, takeaway, don't misread problems. Thank you. And the number of paths that don't go through an edge is simply, like, it's the same formula, n choose 2, for these subtree sizes. no, n choose 2 here and n choose 2 here, where n is the subtree size of both of them. So this is actually very simple. So what we can do is in a tree, okay, that was a really stupid mistake, but in a tree we're going to notice that each vertex has exactly one edge going up from it except for the root. So we're going to use the vertices to represent the edges, essentially. So that means like we rooted at 0, so everything's going to be 1 indexed, so we're going to subtract 1 to make it 0 indexed. Subtree size plus equals val, yeah. So total path equals that. And path v minus 1. If v is greater than 0, because we don't want to do it for the root. Total path minus equals, just copy that. Subtree size minus 1. Okay. And now we're going to just subtract n because we don't care about the number of nodes, we care about the number of edges. That was very stupid. Okay, now we're more wrong. What is with that? What's with that? Is this right, first of all? Oh, wait, okay. Then equals m. We want to fill in the rest with zeros. So we're going to start at m, which means all of these values aren't going to be filled in. Actually, we want to fill the rest with 1s, because sometimes we're using too many. Okay. What's with that? So 4, 3, 3. Well, that's right. Then 3, 3, 3, also right. And that's third one's a bigger number. So what's with that? So we have 8. What are we missing here? It should be n, not m. I'm dumb. 17, 18, 286. Okay. This is kind of dangerous because these samples don't have anything with this case. And if they guaranteed any relationship between n and m, we wouldn't have to do that. But what we should do is have something where we're just making sure we're multiplying right. So let's do that really quick. So let's get a tree of size 4. We'll copy the input tree. And then we'll make like 7. And we'll do 5, 5, 5, 5, 2, 5, 2, 5, 2, 5. Then the answer should be, so it should be 5 to the 5th times 2, 6250 times 4 plus, then we have 2, then we'll stick a 2 here and a 2 here, so that's 6, 25,006. Multi-tests, my bad. Did I do my math wrong? 5 to the 4th. Wait, what is prod? Oh, wait. 5 to the 4th times 4. Yeah, somehow I thought there were 5 5s, I guess. Okay, that's right. 5,012 because it's 2 times 3 plus 2 times 3. Yeah, I'm done. Okay, this is right. I guess we're good. Let us submit. Let's get rid of that. Okay. I guess we have some dumb mistake or something, maybe. What kind of dumb mistake did we make? Well, that is a good question. Isn't it? Are we doing mod right? No, we aren't. So AI less than 6 times 10 to the 4th. Oh wait, so we're clearing edges, reading in X and Y, doing the edges right. Reading in the array, sorting, reversing, so sorting in decreasing order, or non-increasing order. Then we're filling everything else with 1 that we need to. DFS, is this right? So n is small, so that's fine. We're using long longs. Subtree size, long longs for everything. We're doing mod here, that's fine. And path v minus 1 returns subtree size. Okay, subtract n, sort and reverse, so sort in non-decreasing order. So then if m is less than or equal to n, then ants equals ants plus n path I times ai mod mod. And that doesn't overflow. Right? Yeah. For I equals 0, I is less than rem plus 1, I plus plus. Take the product of everything. I'm slightly confused now. What exactly have we done? Okay, I don't care if these aren't primes, it doesn't matter. Just matters that they're numbers and we're using them to test. Alright, comp. Let's make sure we don't have some dumb debug output. Okay, so how does that work? Because we have 8 times 7 times 6 times 5 times 4, and then another 4, so 26880. Then we have 3 times 3 paths go through this edge and 3 times this one, so that's good. That's correct, I think. Is it correct? That would be the question, wouldn't it? It shouldn't matter, right? Like, it doesn't matter where we put the ones, we just need to put them somewhere. Okay, so I'm not sure what this is. Maybe we did some sort of misread or something. Did we? Because it's the same exact formula except we multiply everything. It's just copying a different tree, I guess. And the answer for this should be, so you have 3, 3, 3, 8 times 7 times 6 times 5 times 4 times 3 plus 3 times 3 plus 2, 2,175. Okay. I guess, I don't know, is this some large case or something? What's our execution time? 93 milliseconds. Okay, that's relatively high. So I think we did get to a large case. So we shouldn't have negative modding issues because this is always going to be greater than 0. Turn subtree size. Okay, I mean, I guess we can try some random case and see if we get our runtime error or something. Not really sure what the answer for this should be, but it should be much smaller. Yeah. 8 times 7. Not sure. Okay, this problem is definitely giving me trouble for what it should be. So we read an N, we read in the edges, then we read an M, and we did that. Slightly confused here. So this should be harmless. We're just setting everything that isn't yet set to 1. Perhaps some indexing is off or something. I mean, we're getting right answers for some small cases. That's ants equals ants plus npath I times AI. Both those are less than mod, so we do it modulo 10 to the 9th plus 7, which is what they want. Is there anything else where we would have to mod? Because this is at most n. These are also at most n. So that should not be a big deal. What exactly have we done here? Maybe the indexing here is sketchy or something. It's like if we have one extra element, rem is how many extra elements we have. Here implicitly m is greater than n. So this will be greater than 0. And so we want to take the indices from 0 to rem, then multiply all of those by 0. Like, is my idea of stacking wrong or something? That I don't understand. What exactly did I submit? Did I submit with some weird debug output or something? No, I got rid of cout prod. And I passed these, which is fine. Like, all these numbers are small. And then this is going to go up to n, and I plus rm is going to go up to m. So since m is greater than n, that should be fine. Then npath I is everything else. But is the idea of stacking wrong? I mean, I don't know why it would be. So we want to multiply as big things as possible. The same maximum distribution index. really sure what else we would do. Maybe it is like somehow resetting the. Okay, so we're clearing all of the edges, right? We're setting end path, which means we're not relying on previous values. Setting end path. So n is greater than or equal to 2, which means we're going to have at least 1 and minus 1. Then assuming a lot of people saw this and we're just making a dumb mistake. Okay, let's just move on to E and see what happens. We'll come back to that later, I guess, or if we just can't get an idea for this one. Well, that's annoying. Okay. So maybe we can do line sweep, or we're just supposed to do that. Pretty sure I've written this exact code before. Let me just see. There's some contest on ActCoder that I. What was this? Actually, I don't think it was. Might not have been in contest. I don't think I was doing it on this actual account, which is slightly weird, but. Which one was it? Yeah, it was this one. So this is like a very similar problem, except you have to do more. So let's see. Ignore the name. Alright, it was DSU. And what was the problem? Is it the same thing, kind of? There are many segments. Very sure we could just mess with this code and then eventually. Yeah, I remember this. Okay, so the point of this problem was you're in a region at 0, 0, and you want to find how big the region you're in is at. There was a smarter solution that hinged on n and m being small, but this isn't necessary here. However, this is kind of annoying because it doesn't let you. Okay, I don't think that's going to be helpful. What we have to do is basically, I guess, line sweep, then do some sort of annoying line sweep. Each segment intersects with one of the square sides. Why is that useful? Let's see. So we can merge all of the vertical and horizontal ones. Then we're going to have some sort of structure. We have like a cave, like stalactites and stalagmites. I don't know what to call them. I only have one sample. I guess the strong sample, but still. So I guess you could do it like this. If you have some sort of thing like this, every... Wait, how does that work? No, that's not necessarily true, is it? No, it's not. What I was thinking doesn't work. Oh wait, it does, doesn't it? So my idea right now is to do some sort of annoying like sweep line with, let's say, a segment tree because that's fun. Or like a family tree, it doesn't really matter. The idea is for every vertical segment, like let's say we copy this. Wrong thing. Okay, we're gonna get rid of this because somehow this is wrong. I'm not sure why. It's probably some like one line bug or something. Let's say we put a thing here, right? So it intersects at 3 points vertically. And notably, it also divides things into 2 segments. Or it creates two more new groups. And I think because everything has to touch edges, this is always true. That is, either it'll create a new vertical group or a new horizontal group. No 2 segments on the same line. Wait, that's also interesting. So either we have one that goes up or we have one that goes down. Okay, that's kind of nice. So then, what do we do? So then because of this, let's say we put a segment here, intersects 4 lines, and it creates 3 new segments above. And if we put it here, it intersects 4 lines, and it creates 3 new segments below. So the idea is just to do like sweep line with a segment tree, I guess. So we're going to copy this into some temporary file since it doesn't matter what we do here, and then let's just do this one since this seems easier, or at least nicer, or at least one that I maybe won't get wrong answer on. That's the hope. I have a segment tree template. I'm just going to use that because I have it pre-written already. Then we need, so it's going to time out. We have 2 seconds, 10 to the 5th of each. That's fine. Then we do some sort of sweep line. So we use, so we can just use a Fenwick tree. That's easier. That is indeed easier. Okay, now we do get range. I'm just gonna write helper functions because I'm lazy. X, and this will just remind me to do one indexing. So bit b, then b.init 6 plus, let's say 9, doesn't matter. So plus plus x, then we do bi.add x1 del. None of these are necessary. I'm just forcing myself to use these for one indexing. Return by.query r minus by.query l minus 1. It's fine if we query 0 here since we're just checking if it's less than 0, but if we try and add to a location that's 0, like it's going to infinite loop because this is going to be 0 and we're adding 0 to 0 and that's never going to terminate, so let's not do that. I'll get rid of this. Now, okay, so horizontal we're going to store as just as the representation they give. Pair ll pair long horizontal. Then vertical is given as, we're gonna store these. We're gonna eventually sort them by y, so we want to store them like that. So cn to n to m, then for okay, I'm gonna use this part of my template because it's already written. Basically, it just lets you read into a pair in the order that their things exist, so that's perfect. Doesn't work for this, however, so we need to read into the second one first because we want the x coordinate to be second so that we can sort by the y coordinate, and specifically the lower y coordinate, which is fine. Then sort horizontal, sort for m. So now we're going to do kind of two pointers approach, I guess. Actually, what we can do is we can vector pair LO Q. And this is going to sort events like actually pair LO. Actually, what's easier is, let's do this. So this is going to store an event of, at this y position, add z to a place at this x. So what this means is that event, let's see, var I.f dot push back, what is it? So it would be make pair vari.s1, since we want to add there, and then event vari.s plus 1, since we need to, we're also including this point, since it also matters. Vari.s plus 1 dot pushback, make pair, no wait, vari dot first. This is the other thing about using pairs, and this is dot first dot second. It's the second y coordinate, and then we subtract 1 here. So then the LL point equals 0. Now, for we start off with 1. So then we say if this vertical segment spans the whole square, then it's automatically going to cut into stuff. So we'll be happy there. We're also going to add 0 and add max. Since we want the segments on the ends. I'm actually entirely sure if this works. Automatically start with answers 1, then for every vertical segment that spans the whole square, we're going to count an extra segment, count an extra group for that. It should be good. Then what do we do? For LL I equals 0, I is less than n, I plus plus. While point is less than or equal to what we have here, for I dot first, while we want to apply the vertical segments that come before this and also after this, because right here, here we're going to have an event that says add 1 to this x position, and here, up here above this, we're going to have an event that says subtract 1. So we need to apply all the events in this range, which is what we're doing with this pointer. Point, just make sure to remember that, because I always manage to forget that somehow. For pair LL x event point. If I don't know why we made these functions. They're kind of redundant, but whatever. If x dot second equals 1, add x dot f, else del x dot f. Perfect. Now ants plus equals get range horizontal I dot second dot first dot second dot second. This is just the horizontal range, like that, for example. What did we just do? Okay. Alright, let's test it. Okay. What have we screwed up? Pair. Does it want that? What does it want? Here. I didn't even have the comma. Maybe that'll crash everything. BI. Oh wait, this should be void. Void, otherwise my compiler is going to scream at me. Because I told it to, which is fair. 10. Okay, what's with that? Why What are we counting too much? So here, oh wait, minus 1. We do minus 1 because, like, if we intersect one segment, it doesn't do anything, so we have to intersect at least one. Then, let's just screw with this a bit. Make sure we're doing this right. So we're going to add another vertical segment that has x of, let's say, 8, 0, 1 million. And then the answer for this should be 10. Okay, let's try submitting. Maybe we'll get wrong answer for this too and have a super fun time. Okay. Where are we right now? We have not a great score for E. We're actually not doing terribly. Monogon is also struggling with D, which is fun. So now let's get back to D, and then, how many people solved F? Like LGMs? We have this alt, this dude who's like 2800. Rainbow. Okay, well, yeah, well, we should definitely do D. So that one was an easy E. I really still don't know what's wrong with my D, because I don't know what's wrong with my solution for D, because, like, I don't know. That would be sad, though, because if we had D earlier, we would be doing really, really well. But we're not, so I guess let's figure out what's happening here. So it also kind of serves as a lesson, like, don't be scared to just, like, take a little break from a problem. It's what's known as a context shift, and it can be really helpful sometimes. So now, for example, I can come back to attack this bug that I have with with a refreshed mind. And you don't even have to go out and solve another problem. You can just, you don't have to go and solve another problem. Just, like, take a couple minutes of break, clear your mind a bit, and then come back to it kind of refreshed. So that's actually what I'm going to do. I'm just going to take a minute and, like, not look at this, since I've already stared at this code for a while, so if I'm going to stare at it again, I have to do it in a more productive way. And ideally, we'll be able to fix this bug, move on to F, and see what we can do about that. Okay, let's get back into this. So we have already stared at this code. So n is 10 to the 5th. There are 110 test cases. There are 100 test cases. That doesn't matter. We're reading in the test cases. We're clearing the edges. I think we're doing all of those fine. We start ants to be 0. So what kind of bug are we going to have here? Actually, I started off by complaining about E, but I'm not. Like, they actually made it really convenient to do the implementation without a lot of edge cases, so I'm happy about that. So to the setters, thank you for not, like, making it annoying geometry. Just like regular geometry. Which is still kind of annoying, but I mean, it wasn't that bad to implement once you get the idea. So let's go back to this. We're going to, it's a tree, right? Like, it's a connected tree with n nodes and giving each of them an integer. So each integer must be greater than 0. We're satisfying that. Product of all n minus 1 numbers should be equal to k. We're also satisfying that. And the number of ones must be minimum possible. We're also doing that. So what exactly do we do wrong here? So the general idea is you want to multiply big numbers with big numbers. And big numbers by big numbers. So another way to count these number of paths is actually just it's just, wait, hang on. It's just above times subtree size, since like, we can get rid of this. We have some tree, and we have some stuff to the left of it. Let's like just draw a few edges to go out. Alright, let's say all of these are edges. Then we have these number of nodes, and we have these number of nodes, and we can pick any node on, oh, actually, let's say we're counting this edge. So we can pick any node on this side, and have it go on a path to any node of this side, and it'll go through this edge. Which means, let's say we have x and y here, it's just x times y. Because we have x nodes to pick from this side, and y nodes to pick from this side, and all of those pairs are valid. So really what we can do is above times subtree size, mod mod. Although that really shouldn't make a difference. I don't see why it would. So I don't think that's the fix. What would be the fix though? Seemed. I'm gonna scream myself when I find this because it's gonna be so annoying. So, if m is less than or equal to n. So first of all, we have n minus 1 numbers to place. So we subtract n, then we just put the numbers that we have down. Mi is less than ni plus plus. Set ai to 1. That way, if m is less than or equal to n, some of the numbers are going to be 1. And that's not good. Or some of the numbers are going to be not set. So we want to set them. Like, is it some convoluted thing of not resetting between test cases? Because I don't know how that would work. Since here we're going to set n path to, we're going to set all the numbers from 0 to m minus 1 minus 1, so m minus 2, because 0 indexing, and that's going to be fine. So we're going to set the first m minus 1 numbers to whatever they're supposed to be, not relying on any previous values. And here for m, we're going to read in the first m integers. Then if we need more, we're going to set the rest of them to 1. then here we're going up to n. So n path is going to be fine. Wait, oh my god, okay. Oh, this is stupid. Okay, what we're doing, oh man, that is such an annoying bug. We're sorting the modded version of these instead of sorting them. So if we have, oh man. Okay, this is gonna fix it. Like, here, let me illustrate what we have. So let's say the mod is 10 to the 9th plus 7, right? So let's say we have two numbers, like 10 to the 9th plus 10, and we have 5. So if we, obviously, this one's bigger, but if we mod both of these numbers by 10 to the 9th plus 7, we're gonna have 3 and 5, and so we're gonna think 5 is bigger, than this, because we're sorting them by the modded versions. So what we need to do is sort first, then apply the mods. N path I mod equals mod. Oh, that's so annoying. That's so annoying. Really sad that it took me so long to catch that. Okay. Man, that is a subtle bug. Okay. So we pass. Let's see how we're doing now. Well, I guess a lot of people solve that. What the hell? Is A, C, D, and F? That is very interesting. Okay, so yeah, that is slightly annoying. Alright. Well, I'm sad that we didn't see that bug, but suppose what can you do but not make mistakes again? Hopefully I'll learn from that. Hopefully you guys can too. If you have like wrong answer on pretest 5 or something annoying, be careful with that. So yeah, that was stupid. Let's not do that again. Ever, please. Especially now in a screencast. That'd be nice. Okay, let's do something now. You give an array of link 2 to the n. I know from a USCO problem that it's 2 to the 18th is 262,000, so that's a big number. What? Replace x. Okay, change x to k. Really? Okay. Treep uses. I think this is just straight up a treep problem. Actually, let's see how fast people solve this. 30 minutes, 28 minutes. Solved F before E. 22 minutes. Maybe it's more than just a basic tree problem. I would hope so, because I don't know what coordinator would approve this, but let's see. I don't actually know how to do this really, so. Okay, you can do it with a tree, I guess. Maybe there's a better way, because it's 2 to the n specifically. Since if it was a basic problem, I don't really know how treeps work, so maybe you can just do it with a tree, but maybe you also can't. Also, misspelling subarray. I'm very much hoping that it's better than this, because that would be sad if it wasn't. I also don't want to solve it by just copy pasting in some tree template from online or something, so I'm not going to do that. Okay, so first of all, what are the constraints with the... Oh, wait. Okay. So it's reverse each subarray, which means it's not that trivial, I guess. Okay, good. So for each subarray, 2 to the k plus 1. So reverse each group of length 2 to the k, and then swap Okay. Okay. Good. I didn't really read the problem, so that's on me. You guys also saw I misread D, so let's not jump to conclusions, I guess. Alright, we can delete all of these. That's an unfortunate mistake I've made. Probably cost me a ton of penalty, but what can you do? I mean on D, not on this. So change AX to K. Okay, so they're only like n values of K and n is small. So what I'm guessing we want to do is we want to be able to apply each query quickly. Now how we do this, I don't know. Let's say we have some array with like, I don't know, 1, 2, 3, 4, 5, 6, 7, 8. Then we apply a reverse approach, or we apply a reverse query on this to 1, 8, 7, 6, 5. Then we swap these two, and it's basically equivalent to reversing the whole array, which is one interesting thing. 5, 4, 3, 2, 1. Those ugly numbers, but so a reverse and a swap of length k is equivalent to a reverse of length k plus 1. Wait, what does this do? That's kind of a weird operation. So it's 2i minus 2. Wait. What? Okay, maybe it's not the same. Maybe we got that wrong. So it's 2i minus 2. Let's say I starts at 1. So it's 0. Huh? And 2i minus 1. What does that mean? Does it mean we kind of bubble sort the first subarray of length k, 2 to the k, all the way down? What does that mean? Also, are we in triple digits now? I guess we would be. Yeah, with that rockin' penalty right here. That is just so annoying, though, what I did. Anyway. Okay, let's just look at what happens here. Swap is such a weird operation. so it's 2I minus 2. So it's like 0, 1, 1, 2. Then we move I, and then it's 2, 3, 3, 4. Then we move I again. What happens here? Wait, what am I thinking? These are the... No, it is that. It's exactly that. Yeah, we just switch all these. What am I thinking? Okay, so that's exactly what happens. So we have a reverse, which is gonna like, let's say we call a reverse on this, then we're just gonna reverse each of these. Then we do a swap on these sizes, and it's like 5, 4, 3, 2. So swap K, wait, is it the same the other way around? Yes. It doesn't matter which order we do the operations in. So swap K plus reverse K is equal to reverse. Maybe it is still a treat problem though, because these are very suspiciously like treat operations. Maybe we'll build a weird segment tree. I don't know yet. If we do something else weird, like still going. Something else weird like a swap 2 and then a reverse 4 or something. So we have 2, 1. My guess is that you can kind of bunch up a bunch of operations into one. No, it's kind of weird what happens here. Wait, how is E worth the same as F? Are they really that easy? How many people have solved this now? Are many of these guys trolls? Oh, there are a bunch of people that solved F instead of E. So maybe one of them is just easier for our people. Or maybe this is just easy. I'm guessing so if we do some sort of segment tree, right, then every range we apply is going to be like affected by the queries somehow. So like for example, if we do a reversal that covers the whole, let's say we want to query this, right? So if we do a reversal that covers the whole range, then we just kind of like, all right, this is a bad example. Let's say we want to query this, then we do a reversal that queries the whole range. Then we kind of just flip it so that the new range is like here. But if we do a swap, we have more problems. Because it may be possible to just have it so a single range gets decomposed into like a disjoint. Like, is it possible? What I'm wondering is it possible that like you can have it so you eventually have to query something like this in the original array, like every odd index or something? Because that's not very easy to simulate with a segment tree when you have contiguous ranges that you're interested in. The question is, how many times does a query get split up? And the answer could be many. Time limits, 3 seconds, 10 to the 5th. So maybe there's some square decomposition or something. Definitely can't do something crazy like modes with updates. There's no way that would work, especially for just this weird kind of a problem. It's interesting that there are only n types of, there are only n possibilities for reverse and only n possibilities of swap. But I don't know what to do with that. Very not sure what to do with that. L less than or equal to R less than or equal to the N. Okay, replaces obviously. Maybe there are most log n ranges or something. Something like that. Because it feels like intuitively, it feels like it's kind of hard to split a range up. Or is it? I'm not really sure. Could also be that there are weak pretests and the number of people passing is not. I don't know. Probably not. I would doubt that. Oh, they did fix that eventually, just silently. Are there any clarifications or anything? Or did they just, yeah, they just fixed that silently. Nice. Because there was a small typo there before. Not really getting anywhere with this. So let's try the idea of does it matter the order the queries happen? It must. I mean, it has to. We have 1, 2, 3, 4, 5, 6, 7, 8. Then we reverse the whole thing, and then or first we do a swap, then we reverse the whole thing. Five, 6, 7, 8. Wait, does it matter? Huh. Doesn't matter. Because no matter what, if we do a query, we're going to apply it everywhere. Doesn't matter. Maybe it matters if we do a small one and a big one. Like 2, 1, 4, 3, 6, 5, 8, 7. And we reverse. Which is the same as doing that. Maybe the order of queries doesn't matter. Huh, okay, so what's useful about that? Wait. Can we just say that? Like, out front. Up front, not up front. Like, so we do a reverse here. Because we can't ever take elements like outside of their range. Okay, let's prove it formally kind of. So reverse applies a permutation like this. So for example, 2, 1, 4, 3, etc. And applying a permutation means that you send every number to the index that its value is. So for example, you would do that and that, which is perfect. Reversing is like this. So let's try it for a bigger one. Let's say you have array of length 8 and you do a reverse with length 4. So you'll have 4, 3, 2, 1, 8, 7, 6, 5. And the swap would be 5, 6, 7, 8, 1, 2, 3, 4. I don't know where to go with this, but like, first of all, what's interesting is that these are like almost inverses of each other. Well, actually, if you combine them, you'll get the reverse of a regular permutation, I think. Okay, well, I have no idea how to prove that order doesn't matter, but like, I have nowhere else to go, so we're just gonna assume that for now. Then maybe it'll make it easier somehow. So we're gonna assume the order of the operations doesn't matter, and if it does, then I'm sorry. I will just like if this doesn't get anywhere, I don't know. It's kind of not that intuitive to me, but I'm not sure. So then we assume order doesn't matter. Then somehow we need to like make queries happen. I don't think we're gonna clutch this, to be honest, but we might. So who knows? So we're gonna say lazy is -1. We want a sum segment tree, so we're gonna take that. If lazy I return. I have this weird template, but it's not that big a deal. It's also not that great a template because it doesn't even like let me support certain things. Okay, wait. So lazy is -1. Then if that, 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 eval lazy. Lazy I equals v.val. And lazy I, it's a range set. So we're gonna do that. And we're going to set it so it just sets it to that val. And perfect. Now what? We're going to use PLL because I don't have much time. We're going to stick with the template, I guess. Insert IV. We'll normally not use templates, but since I have 10 minutes left, we kind of have to clutch this. I don't even know what to implement. That's also a problem. So we need to like figure out what each query ends up as. So each query starts off as a big interval, but then like it may get split up over time. So what we can do is hello swap. didn't think we were going to clutch this. There's no way I can write both of these in 2 minutes without flaws. Yeah, even that's not going to work. Okay, well, so the general idea was to... Okay, yeah, there's no way I can do this in 2 minutes because I don't have the implementation power. But my idea was you take some query, and then some operations are going to maybe split this query up. I don't know how it's going to work, but then you have some like disjoint set of queries, and then you can, with a segment tree, apply all of them individually. So my guess would be is because of the properties of the power of 2, like there aren't going to be that many queries that we get, but okay, yeah, less than a minute left. There aren't going to be that many queries that we get. However, I'm not sure of any of this. I'm not even sure if my initial thing is correct, so I don't really know. I guess we'll just, yeah, I'm not sure what to do here. But another thing is because queries orders don't matter, you either have 0 or 1 swap and 0 or 1 reverse operation. Since doing 2 swaps or 2 reverses is pointless, like there are only log n actual queries that you have to apply per replace or sum. Then with the replace or sum, you would figure out the intervals that are represented like in the original array, and then you'll take the sum over querying all of them. It's not that clear. Yeah. There's a lot of people that solve that. Well, let's settle for mediocrity again. Okay. So that's my general idea. I'm not sure if that's correct. So I guess we'll find out later. Okay, let's just go over solutions then. So the problem is simple. You're given a coordinate axis. One of these points is 0, and the other point is a point named conveniently A. Then what you want to do is you want to find some point B. Let's say it's here. Then you want to make okay, A is at coordinate n, and this is at coordinate 0, and this is at coordinate B, whatever it is. We want to make it so the following property holds, that the absolute difference. So first of all, let's let distance of x1 and x2 be just like the distance between them on the plane, or on the line, which is the absolute value of x1 minus x2. That's fine. Then we want to make it so the absolute value of dist 0b minus dist AB is exactly equal to k. Okay, so first of all, okay, so maybe for some inputs like this B, it's not possible to find one. So what you can do is you want to, in one move, you can move A to the left or to the right by 1, and you want to find how many moves you need to make such that there exists such a B. And the way this works is, so if you pick any B first of all, what happens here? So if you pick any b that's greater than both 0 and a, then the absolute difference is just a minus 0 equals a. And if you pick any difference in between, let's say for example here, let's say this is 0, a is 5, so we have 1, 2, 2, 3, 4, 5, and okay, so basically we're going to be no matter what, if this is 5, one of these numbers are going to be odd and the other is going to be even, so the total distance is going to be odd. And generally this is true. If this was 6, then we're going to have either 2 odd numbers or 2 even numbers, so the total distance is going to be even. So then we can get, let's find the sum of distances we get for putting b everywhere. So we have 5, 3, because this is 4 minus 1. This is 3 and 2, so this is 1. This is also 3 and 2, so that's also 1. And this is 3, and this is 5. So essentially we can get any odd number that's less than or equal to a. So we can get any odd number less than or equal to a. Which means that it's optimal to have a as large as possible. Like there's no reason to move a to the left. We want to make it farther away if it's necessary. So first of all, if we're not the same parity, let's just move. So if a and b are not the same parity, which we can check with like a mod 2 is not equal to b mod 2. If a and b are not the same parity, we'll move a over by 1. Now they are the same parity. So because we can get any odd or even number less than or equal to a, we just need to increase a until it's the same as b. So the implementation is simple, and I'll go into my code for this. I got a new message. So first, if the parities are not the same, then you increase the value and you make a single step, and then either you have to move a some distance over, or you already have some number, or b is already less than or equal to a, wherever a is. If you moved it, it would be a plus 1 as in the input. Then, so if this is true, you don't have to move it. Otherwise, you have to move it by a minus b. You can combine those because a minus b is negative. Wait. Sorry, b minus a. You can combine those by saying b minus a is less than 0, 0. Otherwise, a minus b. It's like a piecewise function. And you can combine these by just taking the max of 0 and b minus a, which is, or k minus n. So the answer is, first you move it by, you increase it by 1 if the parities are not the same, then it's max k minus n, 0. And that's it. That took a while, but that is how it is. Then let's go on to b. Now we move on. Okay, b is basically casework. Although it's not that bad casework, so it's fine. You have a sequence with 0s, 1s, and 2s. You're not given the actual sequence. Alright, sorry, you have 2 sequences. Let's call them A and B. And they have the elements 0, 1, and 2. Consider this a set. So then, so you're given the number of 0s, 1s, and 2s each thing has. So for example, this is 2, 3, 2, and this is 3, 3, 1. So the sequence A would be like 0, 0, 1, 1, 1, 2, 2, and B would be 0, 0, 0, 1, 1, 1, 2. And it doesn't matter what order they're in. What you're going to do is you're going to reorder it. So like you can just swap make whatever swaps you want, and you're going to reorder it. Then you're going to create a new sequence C, and this C has like special properties. So for each position, for each index I, if the two elements are the same, you're going to make it 0. I'm going to add a few more here. 2, 1. No, wait. 1, 2, 0, 1, 0, 2. So if the two elements are the same, you make them 0. So all of these will be 0. If AI is greater than BI, then you make it AI times BI. So in this case, it's 0. In this case, it's 2. And if we had 2, 0, it would also be 0, which we'll just add right now. And if AI is less than BI, then it's negative AI times BI. So this would be negative 2, this would be 0, this would also be 0. So as it turns out, there are only two cases that are interesting. A pair with 2 and 1, which gives you plus 2, and a pair with 1 and 2, which gives you negative 2. So what you want to do is, you want to maximize these and minimize these. So how do you do that? Well, first of all, let's just maximize these. So let's count the number of 2's we have in A, and then count the number of 1's we have in B, and then just take the minimum of those, because we can't make more pairs than the numbers we have. So it's minimum of 2, 3 times 2, which is 2 times 2, which is 4. Then what we want to do is we want to pair these remaining 1's. We want to pair these 1's in A and these 2's in B with anything but each other. Right? So for A, let's try and pair it with the remaining number of things we have left here, because we don't want to have 1's that we pair with these. And similarly, for this 2 and B's, we're going to try and pair it with anything that isn't a 1. So essentially, after we make the pairings to increase our answer, and we decrease those, so now these become, what would they be? 0, and this would be 1. Then we subtract as many things as possible. Like we subtract the sum of these two from this, and subtract the sum of these two from this. If we go negative, it doesn't matter, because if we go negative, it means we can't make any pairs anyway. So now what we would do is we would take the maximum of 0, and then the minimum of the two new numbers we get after subtracting green from green and blue from blue. So we're going to say minimum of the count of 1's in A and count of 2's in B after subtracting, and then times 2. In the case of this sample, it would be 0. So then we get 4 minus 0 equals 4, and that's our answer. So we basically add as many things as possible. Then we try and reduce the amount of things we subtract as much as possible. If this casework I did doesn't make sense, you can also check on my code. It basically does the same thing. Oh, nice. There are some system tests going on. We have A, B, and C already. Okay. Where are we right now? So we weren't actually doing that bad in terms of speed, but then we just totally died on D. That was not good. Anyway, now we're on to C. So, oh my god, so many tags. All the tags got duplicated for some reason. That's kind of weird. I don't really want to mess with that though, because someone else might. Okay, this problem was actually kind of cool. This is C. Let's do this. And you're given an array. Let's take the sample. So 4, 3, 6, 6, 2, 9. And so first of all, you want to find the minimum element in the array. So the minimum here is 2. Then you want to say, you can do a bunch of operations to this array. So in one operation, you will pick two numbers, then take their greatest common divisor. I'm not going to define what a greatest common divisor is. It's basically the biggest number it's basically the biggest number such that both of these numbers are divisible by it. So in this case, it will be 3, because 3 divides both of them, and there's no bigger number that does that. Now, if this greatest common divisor, GCD, is equal to the minimum element, then you're allowed to swap these two. Otherwise, you can't. Your goal is to sort the array. Or actually, your goal is to determine if it's possible to sort the array or not. You don't have to print the operations, but I mean, it's not that big a deal if you do, but you don't. So how do we do this? Actually, it would be kind of more interesting if we had to print the operations, but it's not. It's just kind of tedious adding implementation, so not really. So how do we check this? Well, first of all, let's check each element and see if it's a multiple of 2, or the minimum element. So this is, this isn't, this is, this is, this isn't, this, or this is, this isn't. Right, so any number that isn't a multiple of 2 obviously doesn't have 2 as a divisor. So no matter what we do, no matter what we pair it with, it's never going to be 2 that's the GCD, because it's not even a divisor of this number. So therefore, anything that we mark with a 0 here, we can't move. We can't touch it. They're rooted in place. Now, what I'll show now is that everything we mark with a 1, that is, it's divisible by that, we can sort. We can sort all of the 1s relatively into non-increasing order. So for example, we can sort it like 2, 4, 6, 6. And how do we do this? Let's do I don't remember what it's called. I think it's selection sort. So first of all, let's move 4, 6, 6, 2. Now, notice first of all that the minimum element, the GCD of the minimum element and a multiple of that element is going to be the minimum element. So we can swap this with any other element that's marked 1. So let's see. First, what we can do is, let's move 2 to the very end. Okay. Now, in this case, it's already there. So now we're going to swap 2 with the biggest element, like any of the greatest elements. So for example, we'll make this swap. Then we'll have 4, 2, 6, 6. Now, we know that the biggest element is at the end, so let's do the same thing. So now we've sorted this part of the array. Now we're going to move on, so we'll move 2 into this position. Even though the maximum element is already here, it doesn't matter. This is just this is a universal algorithm. So we're going to ignore this part since it's already sorted. So we have 4, 6, and 2. So now we swap 2 with the biggest element, and that would be 6. So we make this swap again, kind of redundant, but it doesn't matter. We have 4, 2, 6. Now we know that this is sorted, so now the last 2 elements is sorted. Now you can see where I'm going here, right? The algorithm is simply to move wherever 2 is, we move it to the last position, and then swap it with the element that's the biggest. And that way we're going to sort the array by putting the biggest element down in the last position, then the next biggest in the next position, then the next biggest in the next position, and so on. And then finally we'll put 2 in the first position since it's the minimum. And that's it. So we can always do operations like that, and we can always sort all of the 1s relative to each other. So now, in terms of implementation, all that means is you let's say you put all of the, let's say you make a vector with all of the numbers. And then you're going to also make a vector with the corresponding indices. So this is index 0, 1, 2, 3, 4, 5. So the indices of the 1s would be 0, 2, 3, 4. So now we'll sort these. So we're going to sort this, and it becomes 2, 4, 6, and 6. then we'll just put them back in the indices. So 2 will go to index 0, 4 will go to index 2, 6 will go to index 3, and this 6 will go to index 4. So we replace the array with 2, 4, 6. I know that's the same, I'm just illustrating a point, and 6. So this is our final array. So we have 2, 3, 4, 6, 6, 9. Note that it's always okay to sort all of the ones no matter what the configuration is. Because like if it's not possible, it still won't be possible if we sort all the ones. And if it is possible, then we'll want to sort all the ones anyway. So now the implementation is simple. We just check if the element is sorted. I think there's like a C++ STL function for that. Like it just straight up checks if a thing is sorted. But it doesn't matter. Basically, if an array is not sorted, then there's going to be one element that's bigger than an adjacent element. So for example, if we had 2, 4, 3, 6, 6, 9, then this element would be bigger than this one. So we just check for each pair of adjacent elements if any of them is bigger than the one after it, and if so, it's not sorted, otherwise it is. And that's the implementation. So in conclusion, we mark everything with 1 or 0, 1 if it's divisible by the minimum, 0 if it isn't. Then we sort all the ones, which we just showed that we can do constructively. Then we check if the final array is sorted. And that's it. Check my things that passed. Okay, still in queue. So now we go to D. D is annoying, or it annoyed me because I made a stupid mistake. It's not exactly an annoying problem, I just had trouble with it. I'm not happy that I had trouble with it. Okay, so you're given a tree. I hope you know what a tree is. If you don't, I don't know how to explain it. I don't know how to explain what graph theory is. Like it's a set of vertices and edges that connect these vertices. A tree specifically is a special case that has a bunch of properties. So a tree has n minus 1 edges. So you're gonna assign an integer. You're gonna assign an integer to each thing, to each edge. For example, 2, 3, 5, 7, 2. This happens to not be optimal. We'll show why later. And you want 3 conditions to satisfy, to be satisfied. First of all, everything must be greater than 0. The product of, this is a pi symbol, which is product. So the product of all AI is equal to some number k. And final condition is that you have to minimize the number of ones. And then, so for example, if we did make this 1 and make this 10, that would not be optimal because there's a better way to do it which doesn't use as many ones. So, one thing that's important is that k could be huge. So we're not actually given k, we're given a bunch of prime numbers such that their product is k. And the fact that they're prime is important because it means you can't divide them anymore. So like if you have less than n minus 1 numbers, like some of them are going to have to be 1. And if you have more than or equal to n minus 1 numbers, then it's guaranteed that there's some way that you can make it so none of them are 1, so you have to do it that way. And that's kind of important. So now we're trying to maximize a function. Basically, they define f of u and v to be the path sum from u to v. And what that means is, like you pick 2 vertices, And then you take the sum of the edges on the path between them. For example, this is 5. This is 12. This is 3 plus 5 plus 7, 15. And you're going to take this value for all paths. So for example, you'll take this vertex and then you'll do the path that goes from this to every other vertex. And then you'll go to this vertex, and you've already looked at this vertex, so you won't take this path again, but like it's all unique paths essentially. And then we'll go here, and then here there are no unique paths, so that's fine. Here the unique paths are here. Here no unique paths. Here no unique paths. Yeah. So another way to think about it is it's just the sum from I equals 0 to n minus 1, 0 indexing. I guess n minus 2. And then the sum of this sum from j equals I plus 1, so excluding the path from I to I plus 1, n minus 1, of f I j. So it's every unique path, essentially. Yeah. So how do we minimize this? Let's redraw this tree because it drew circles on it. Okay. So one common techniques is one of the common techniques that's used in competitive programming. When you're trying to think about some function or something, either you want to compute it or you want to minimize it, is contribution to the sum. Now, what does that mean? Well, what it means is, instead of counting the sum of all edges over all paths, we're going to count how many times the value of each edge is counted. So for example, let's say this edge is A, this edge is B, this edge is C, D, E, and F. We're going to count the number of times A is counted, plus the number of times B is counted, plus the number of times C is counted, etc. Now this is convenient because we can actually easily find out how many times each edge is counted. Like let's consider the vertex D, for example, because we're doing the problem D. And the edge D, not the vertex. So we're here. We have 4 nodes on this side and 3 nodes on this side. So any path from a node on this side to a different node on this side is not going to go through this edge. But any path from a node on one side to a node on the other side has to go through this edge. So how many paths are there from a node on this side to a node on the other side? Well, you have 4 nodes on this side, and then for each node you have 3 other nodes that you can stop at. So it's just 4 times 3. And that's it. So the number of times an edge is counted is the number of nodes on one side of it times the number of nodes on the other side of it. The implementation for doing this is basically counting subtree sizes. Like say we have the root, let's say we have the tree rooted here, and then we do some DP. This is simple. You can check my code if you don't understand how to do it. For computing subtree sizes, actually, like it's size of x equals the sum over all u that are children of x So u is an element of the set of children of x, size u, and then all that plus 1 because x is a vertex itself, so it counts. Okay, now that's how we do that. And then, so that's the size of the subtree below it, and then like everything else in the tree is going to be on the other side. So the other thing is, it's just n minus size of x. So to count an edge, we count the subtree size of the vertex below it, and then it's just n minus whatever that is. So the formula, the explicit formula is m minus size x times size x, and that's it. So another bit of intuition is that, like, let's say we have four numbers, 7, 5, 3, 2. What's the best way to multiply these numbers to maximize the sum? Let's say we did 7 times 2 plus 5 times 3. Right, so this would be 14, this would be 15, sorry for that 4, and that total is 29. Right, so let's say we did something else. 7 times 3 plus 5 times 2, 21, 10, 31. But if we did 7 times 5 plus 3 times 2, then it's clear this is 35, this is 6, this is 41. And so this kind of intuitive thing, like, the idea is you want to multiply big numbers together and small numbers together rather than multiplying big times small. And the reason for that is, like, you want to maximize the number of times you get a 7, because 7 is the biggest. Like, you don't want to maximize the number of times you get a 2, you want to maximize the 7 because 7's bigger. So bad at drawing circles, like I'll just cut the entire number in half. Yeah, so the way we do that is we pair the biggest number to the biggest number. Then we pair the next two biggest and so on. Alright, so first we have the condition that we want to minimize the number of ones. So, but at the same time, we want to pair big numbers together. So there are now two cases left to this problem. Either m, which is the number of prime factors you're given, is less than or equal to n minus 1. Then let's redraw a tree. Here, 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 and here. Now, the way we assign these is, so I'll label each edge with the number of paths to go through it. This is 6, this is 2 times 5, which is 10, this is 12, this is 6, this is 6, and this is 6. I just did that quickly with multiplication. It's just like the same formula we just did. And now m is less than or equal to m minus 1. So it means, like, let's say our prime factors are like this: 7, 5, 3. And that's it. So k is equal to the product of these, which is 1 and 5, but that doesn't really matter what k is. So again, we want to assign big things to big things. So we assign 7 to 12. Then we assign 5 to 10, and then we assign 3 to any of these 6s. And then the rest of these have to be 1s because we don't have any more prime factors to hand out. So if this case is true, then, like, essentially we just greedy assign the biggest things possible to the biggest numbers possible, and the rest of them get 1s because we don't have anything else to give out. So otherwise, we have another case where m is greater than n. And again, we still use the intuition that we want to multiply big things with big things. So the way we do this is, first, let's give the smallest things. Actually, let's say we have factors like this. So we have 13, 13, 11, 11, 7, 5. All of these are primes, they're just big primes. And I'm giving them a reverse order because, like, that's just convenient to think about. And it's also easy to sort them in reverse order anyway. So what we do is we want to give the biggest number possible to this 12. Like, we're gonna have to multiply some of these numbers together and then give them to vertices, right? So if we multiply 13 by 13, 169, and 11 by 11, 121, and then we give these to each, then, like, you can just see it's gonna be way better to give this bigger number. I can't multiply that in my head. 1859 to 12. Like, you can just think about that. It's going to be way better to give that than 169 to 12 and 121 to 10. And essentially, this is the intuition that works. Wait. Okay, 1859. That is, in fact, a 5. So Well, first we have to give out n integers in total. So let's give the last n minus 2 integers to the smallest ones in increasing order. So for example, we'll give 2 here, 3 here, 5 here, 7 here, and 11 here. That way we still give big things to big things. And then we give the remainder, the product of the first, what would it be? M minus n minus 1, no. M minus n minus 2 integers, the product of those to the biggest number. 1859 here. And that's our strategy. And of course, the way to come up with the strategy is just to have that intuition. You want to multiply big things with big things. You want to multiply as many big things together as possible, then you'll have bigger things. And that's how you kind of solve this problem. If you don't have that intuition, this problem will be kind of hard. But hopefully now that you've watched this, at least it makes sense if you didn't understand it before. Now there's one mistake that got me for a while. I got wrong answer on pretest 5. And I passed system tests and everything. That's good. So I got wrong answer on pretest 5. And it's not going to let me see the test. But the reason is that, like, when you sort values, you have to sort the actual values. But the mistake I made, which I also describe here, is that if you sort, well, you have to take the numbers mod some big number like 10 to the 9th plus 7. But you don't want to sort the remainders. You want to sort the numbers themselves. So for example, let's say you have, I'll give the same example as before. You have 10 to the 9th plus 10, and then 5. Now obviously this is bigger. But if we take the remainders, then we're going to have 3 and 5 here. So if we sort by these remainders, then we're going to do it inaccurately, because 3 is less than 5. So what we want to do is, we want to compute these values, then sort them, then take them remain to the modulo. And I'm sure like nobody else, not many other, I don't know, maybe other people made this mistake, but like, it's kind of a careless thing to do. By the way, this is a 9, not a 4. Yeah. So just don't do that. Beware. If you got wrong answer on pretest 5, maybe that's also what happened. If it's not, I'm sorry. I don't know what your bug is. So, yeah, that's that. Let's do E. E. I'm just gonna steal the sample because it's like it's like they already visualize it for me. So, select here and copy. Okay. In E, you're given a big square. Wait, make this a bit smaller. In E, you're given a big square, and doesn't really matter. Okay, whatever. In E, you're given a big square of size 10 to the 6th by 10 to the 6th. That's fixed. Like, it could be anything. It just happens to be 10 to the 6th. And in fact, it's important that it's 10 to the 6th, although not really, although it kind of is, although it isn't. So, yeah, that makes sense. So, and you're given a bunch of vertical and horizontal segments. You're given that each of these segments are fully within the square, like they're not like this, and they're not like this, that is, they touch at least one side of the square. They can also touch multiple sides. For example, like this one does. Given these segments, you want to find how many different regions the square has. So they already do this counting for me. You have 1, 2, 3, 4, 5, 6, and 7. Now, how do you do this? Well, the way to do this is simply notice. Let's say you have, I'll draw a different square. You know, it's not a square, but it's a shape. Let's say you have this, right? Then you have some line that goes like this. Now, what it does is it intersects at 2 points. And this is important. The fact that each vertical line always touches at least one side of the square is very important. Because it means that when you have a line like this, if you have some horizontal line that touches 2 points, it's going to divide the square into whatever's below here and whatever's above here. So it's going to create a new region. Let's say you have the same thing. This line is going to create a new region here. And if we have it touch 3, then it's going to create 2 new regions, one for each of the intersections. So more generally, and also, even if it intersects both a vertical and a horizontal one, it creates one segment here, and then another segment, another region somewhere else. Like it'll split whatever's going on here and whatever's going on here, because of the fact that all of these have to touch the edges of the square, or rectangle in my case. So this is what we notice, that every horizontal segment, its contribution is number of vertical intersections minus 1. Because if it intersects nothing, then it doesn't do anything. But if it intersects 2 points, then it'll create 1 segment. And if it intersects 3, it'll create 2. And if it intersects 4, it'll create 3, etc. So it's the number of intersections minus 1. And there's one other case we have to consider, that a vertical line goes from the bottom of the square to the top. In that case, that just obviously it creates another region by itself. So that's another special case we have to check for. So the answer is 1 plus the number of verticals that go from 0 to 10 to the 6th plus the sum over all horizontal segments of number of intersections it make with vertical ones minus 1. There's also some convenient other constraints that there's nothing like this. Every vertical and horizontal line has exactly 1 segment. What I mean is something like this and like that. That's kind of annoying to deal with. Similarly, there's nothing like this for vertical. So that's cool. And and as an extension of that, no segments, there's no horizontal intersections. For example, like this. So now we need to count this. So, we can break this into 3 parts. Okay, 1, it's 1. It's 1. Then the number of vertical segments that span 0 to 10 to the 6th, you can just count that by checking for them in the input. Just as you read in a segment, see if it goes from 0 to 10 to the 6th, and if it does, add 1 to the answer. Then you want to find the number of intersections. This is not as This is not as easy. The way you do it is with some sort of some range query structure, let's say a Fenwick tree or a segment tree or anything really. Yeah. So let's look at a single vertical segment. So this vertical segment is at x position 2, and it goes from 0 to 5. So that means in the range of y 0 to 5, let's say we have a Fenwick tree that's like this. So initially everything is 0. Then the keyword here is sweep line, that we're going to change this to 1 if at our current y position there's a vertical segment that goes through here. So for example, here, on the y range from 0 to 5, we're going to set 2 to 1 in that range. And then once we go above it, say 6, this segment doesn't matter anymore, so we'll set it back to 0. Yeah. So we can kind of keep a list of events. Say we're going to go up, right? We're going to sweep up through the array. So that means when we get to the beginning of our vertical segment, we want to add 1 to its position. So we have a command that says at position 1, add 1 to position 4, for example, or position 3. Then we have another command here, so we're going to count this segment. So it's really like saying at 10 to the 6th plus 1, remove 1 from 3. Sorry for that handwriting, but that is a word from, and this is a 6, even though it doesn't look like it at all. So that's what it means. So basically, we can just iterate from 1 to 10 to the 6th. So like, let's just go here, right? Then we're going to apply all the updates that we say we have to do at this y-coordinate. Then we're going to check if there's a horizontal segment here, and there isn't. Then we query the Fenwick tree for the x range it covers. So there are events here. Here we add 1 to 2. So let's keep track of this. I guess we can dry run it. I don't know. So here we add 1 to 2, and here we add 1 to 4. Now we're done. Here, nothing happens. Like, we don't have any events, and we don't have any segments. So here, first, oh wait, actually, sorry. Here, this segment begins. So we have 1 here. We add 1 to that. Then here, oh, also this is 1, and the one on the end is 1, because these also count as intersections. So then here, this segment ends. So here we stop caring about the segment. So we change this back to 0. Then here we also have a horizontal segment. So we query the range from 3 to 10 to the 6th. Here there are 2 intersections, so we add 1 to the answer. So we continue. Let's go here. All we have is this horizontal segment. And here we have 4 intersections, which means we create 3 new regions, which is cool. That is, we intersect here, 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 and here. So we'll add 3 to the answer. So now here we have another horizontal segment. And this has 1, 2, 3 intersections. So we add 2 to the answer, which means in total we've added 6, and we have plus 1 for the whole square, so we have 7, which is the answer for the sample. Then here, nothing happens. Here, this segment ends, so we replace this with 0. And at the end, and eventually we'll just go up to 10 to the 6th, and then we'll be done. Yeah, that's it. And of course, remember to count the number of like vertical segments that cover the whole square. Why paint? Why would you not let me scroll? Okay. So like for example, this would add, we would initially add 1 to the answer, and because we contribute 2 more intersections here, this would add 3 to the answer in total. So the answer, if this were here, would be 10. It's always good to like test edge cases that aren't in the samples if you think they're edge cases, just in case like your code doesn't actually work. Which is what I did in my testing. I added that line to the sample, and it worked. Okay. So now I think system testing is done. So let's check. I don't think my rank would have changed because it seems like not many people failed system test. Yeah, probably not. I don't understand why E and F were worth the same amount of points. Because F seemed way harder to me. Although it might have been easier to other people, I guess. Alright. So, I have a general idea for F. I actually don't know if it's correct, so I'm not really gonna... I'm just gonna say idea. The problem's kind of complicated, so I'll let you read it on your own. And basically my idea is... So again, this may not be correct. Order of queries doesn't matter. I also don't have a way to prove that. So maybe take everything I'm saying with a grain of salt. So order of queries doesn't matter. Then this we can show. A swap of length k plus a reverse of length k equals a reverse of length k plus 1. I don't know if it makes that big of a difference, but it might, so it could be important. Then you only need to you either make 0 or 1 swaps like of each operation, for example. So 0 or 1 swap for each k. So because order of queries doesn't matter, like if you make 2 swaps in a row, they'll just cancel out. And if you make 2 reverses in a row, it's the same thing. So you only need to make 0 or 1 swap or reverse operation each time. So you can kind of like count that. This says 0 or 1. So you can kind of count those and then apply them. And then, so the final idea is, say you're given some interval for a query, right? Now, what the swaps and reverses are going to do is they're going to like do something to this interval. They're going to like change it, maybe split it up a bit. And so I'm not sure how true this is, but I think there aren't that many disjoint intervals. Maybe, like something like O of log n or something. Again, I have no proof for this. This is just what my intuition is kind of saying. Then, so for each query over an initial range of the array, you can basically apply these operations and see what it does to the query, and then you'll take the sum of like a segment tree query or something for all of these values. And the same thing for input, and the same thing for like change, you'll just follow where it goes, and then you'll change that element in the original array. Actually, maybe you'd have to reverse it kind of. Like you'd want the positions, you want the set of intervals in the original array so that you can build a segment tree on that. And at the same time, you want to figure out where this goes in the original array. So if it like ends up here, if it would have ended up here without having done the operations, then that's that. But since, like, it's the same thing since each operation is its own inverse, so it's essentially the same as applying each operation and seeing what it does to your intervals. Okay, that was, again, that's just an idea. I can't prove any of this, so I might be totally wrong. Seems like I'm kind of cursed when it comes to div2s. Like, I never managed to full solve. I'm always 1 or 2 problems off, which is kind of sad, but, whatever. It's not like they're rated for me or anything. So, that would be it. Yeah, that's basically all I have. Went over solutions. We're going to have some more contests coming up soon enough. Tomorrow there's an @coder, and then an @coder beginner contest, I think. Then after that, we're going to after that, there's going to be a cook-off on CodeChef, which we'll do. 2 days later, there's going to be the edu, and then round 666 eventually, which I'm not going to screencast because I want to focus really on rounds that are rated, but I will give solutions for that later. And we'll see what else happens in between then. Yeah, I guess eventually we'll try and break this curse so we can finally just, get it. Always seems like we're walled off at the last problem, which is kind of sad. But yeah, that's all I have. Hope you enjoyed this, and goodbye.